Okay, so picking up part 2 of homework 3-4 here. Questions 9 and 10 are the only two we have left. So question 9, we've got a block B which is resting on a surface that does have friction, and then the ropes are all massless. They give me the coefficients. What is the maximum mass of block A for which the system is in equilibrium? So they're saying it's in equilibrium, and I want to know what's the maximum right value for this block. Well, the key here is all of these are going to be related, and they're actually very similar to a stoplight problem. So those problems we've seen before where we had tensions involved and we knew the system was at rest. Going to be very, very similar to that. The key though is if I'm looking for the maximum mass, I ultimately want to know what's the maximum force that block B can be providing through friction. So really what I want to start by finding is just kind of thinking about this whole situation first maybe. So I've got this tension, I'll call this maybe T1, which is pulling off to the left this way, and it's pulling to the right on block B. I have this third tension here. I'm going to call that T3, and then I've got tension 2 pulling down on that intersection, but pulling up on block A, right? So I've got those three different tensions. Well, again, I said this is like a stoplight or a cable problem because if I look at this, if I break this up into components, right, T1, the only other horizontal force with T1 is the cosine component here of T3, right? So I actually know a relationship there. It tells me T1 and T3, if the system's not moving, T1 would have to be equal to the cosine component of T3. Similarly, right, T2, the only other vertical component other than the sine component of T3, those two would have to be equal and opposite. And again, that was a sine component, excuse me. So T3 sine of theta. So I've got those two relationships, which ultimately I can use if I need to. But that just kind of gives me a feel for what's going on here. So again, if I want to find the maximum mass, I want to find out what the maximum this tension can be, which means I need to figure out what's the maximum that friction can resist that. Because if I focus on block B, well, block B is going to be at rest as long as my static friction can match tension. So that's really the route that I want to start with. Let's find the maximum static friction, right, that we can find. Well, static friction is just the coefficient of static friction times the normal force, which is easy enough because it is a level surface, and they give me the coefficient of static friction. So 0.60 times the normal force, so 20 kilograms times 9.8, because the normal force would, for this problem, right, be equal and opposite to the force of gravity. So that's why I'm using 20 times 9.8. So I can calculate that number, and I end up, when I do so, get about 117.6 newtons. So my maximum frictional force ends up being about 117.6 newtons. So then what that tells me is, well, T1 can be 117.6 newtons. Okay. Well, what that tells us then, right, if we focus on our relationship over here, again, I'm going to kind of blow that image up with this intersection. I've got T1, which I know is pulling this way. I've got T3, which is pulling this way, and then I've got T2, which I'm saying is going downward, right? Obviously not to scale there because I haven't scrolled down yet. Let me do that a little bit. But anyway, I've got these three forces interact. Well, I know, again, breaking this up, that the cosine component of my angle would have to be equal and opposite to T1. So the second I found out that T1 over here was 117.6, that tells me this component is also 117.6, which would allow me, if I wanted to find my third tension. However, since this is a 45-degree angle, and I know it's a 45-45-90 triangle, doesn't that also tell me that if this is 117, this has to be 117 too? So this would have to be 117.6 newtons, which means then my vertical tension here has to be 117.6 newtons as well, right? So because that's a 45-degree angle, I actually figure out that all of those components end up being individually 117.6. The reason that's helpful is if I'm looking for the maximum mass of block A, well, I now know that tension is pulling up with 117.6 newtons, and if it's not moving, the force of gravity better be equal and opposite to that, so that gives me a route to solve for my mass. So the force of gravity on block A equals 117.6, so mass of block A times gravity equals 117.6. So obviously then just divide both sides by 9.8 by gravity, and we do that, we get a nice clean 12 kilograms, right? It's a nice whole number there, but it ends up being 12 kilograms. So that's the maximum that block A can weigh to keep this system in equilibrium. So hopefully this wasn't too bad. Again, it's very similar to a stoplight type problem that we've seen before. Okay, so question 10 here is definitely a tricky question. It's probably one of the toughest ones we've seen, obviously both on this homework and throughout the whole unit. So make sure you do follow along with me as I go through this. If you have any further questions, don't hesitate to come find me and ask, because this is a tough one. But anyway, find an expression for the magnitude of the horizontal force. So I'm trying to find this force in terms of like mass 1, mass 2, the angle, and gravity. Right? So find an expression for that in terms of these other variables. Right? We want that expression though such that M1 does not slip either up or down the ramp. We will assume that all surfaces, are frictionless. So the way that I want to approach this problem is I want to think about mass 1. Right? I'm going to start by focusing on mass 1, and obviously both of these are going to come into play here. But again, I'll start by focusing on just that first mass. So I'm going to redraw my picture just with a focus on mass 1. So here I've got block 1. Well, if block 1 isn't slipping, right, then I know it's in equilibrium. But what are the only two forces acting on block 1? Well, regardless of whether the system is moving or at rest, the only two forces that act directly on block 1, right, this force doesn't act directly on block 1. The only two forces that act directly on block 1 are its force of gravity, so the force of gravity of block 1, and then the normal force between the plane and the force of gravity. So this is where this question gets tricky. These are the only two forces acting, but I don't want block 1 to slip down the ramp, right? And we know in any normal situation, right, if those were the only two forces acting, then normally, no pun intended here, but normally the normal force is equal and opposite to this component of gravity, which means that the block would be accelerating down the ramp. Well, again, the reason this question is trickier is because by adding this force over here, we're actually increasing the normal force between the surfaces. So the normal force between the ramp and the block is actually now greater than the force of gravity. So this normal force here is now larger than the force of gravity. So if I start to think about this in terms of components, right, well, the key is, right, thinking about our angles. So let's go ahead and kind of break our diagram up here in my angles. So I've got theta here. I would have, if I drew in the perpendicular line going straight up, let me try that again to make that relatively perpendicular. So if I drew in this perpendicular here, this angle would actually also be theta. A little bit of geometry could show that, right? Because if I drew in a line that was perpendicular to the surface down here, I know that this angle would be theta, and therefore the vertical angle across from it would also be theta. Okay, so I'm going to get rid of that just so it doesn't get my picture too complicated. Okay, but I do have the angle of theta up here to work with. So the difference is, rather than saying that a component of the force of gravity is equal to the normal force, I'm actually going to say that a component of the normal force needs to be equal and opposite to the force due to gravity, right? So I'm actually going to say that the cosine component, based on this being the adjacent side, so my normal force times cosine of theta needs to be equal and opposite to the force due to gravity if this block isn't moving, right? If that block's not moving. So then similarly, right, my net force on block 1 would then be coming from just this component right here. Okay, so the normal force is coming from that, and then the net force on block 1, in this case, would be coming, because these are the only forces acting, the net force would be coming from just this component, which would be the sine component of the normal force, right? So maybe I shouldn't call that net force 1, maybe I'll just call that F1. So this is the net force acting on block 1, and it's just coming from the sine component of the normal force. Well, this gives me a system of equations that allows me to solve for the acceleration, right? This gives me two different relationships. So the normal force, which I don't know yet, and I won't necessarily find this, so I may get rid of that. So let's go ahead and solve for the normal force in terms of measurements that we do know. So normal force times cosine of theta equals mass 1 times gravity, right? Just Fg, so mass 1 times gravity. So then the normal force would equal mass 1 times gravity divided by cosine of theta. Well, then if I substitute that into this equation, right? So if I take this and plug this in for my normal force over here, I get that my net force equals mass 1 gravity divided by cosine of theta times sine of theta, right? I'm plugging in for the normal force, but then I still have that extra sine of theta hanging around. So then when I look at this situation, right, well, breaking up the force, the net force here, this would be force, the mass 1 times acceleration, and then mass 1 times gravity over cosine theta times sine of theta. We can actually clean this up pretty nicely, right? Both terms have mass 1 in it, so I can cancel that out. So the acceleration of the system that I actually need ends up being g divided by cosine theta times sine theta. Or better yet, if I have a cosine theta on bottom and a sine of theta on top, this ends up being g times tangent of theta. Right? Just a little simple trig there for you. So the whole point of this, the whole point of what I've done so far, again, the normal force had to be more than the force of gravity. I matched the cosine component of the normal force to gravity, and then I said the net force then would come from just the sine component of the normal force. So that's all I did so far. The vertical forces are equal and opposite. This horizontal component here, which is not balanced out by anything, provides the net force. That gave me two relationships to solve for the acceleration of the system. Now that I know the acceleration of the system, I can think about what force I need to apply to the ramp such that the ramp creates that acceleration of the system. So really at this point, I'm going to think of the system of those two different objects as really just one block, as one mass. So I've got mass 2 and mass 1, but if I want to think of those as a single object because I need to get that entire system accelerating with this, well then the force that I need to apply would be force equals mass times acceleration, right? Well, I know the total mass of the system would be mass 1 plus mass 2, and I know the required acceleration to keep mass 1 from slipping needs to be g times tangent of theta. So then my force is as simple as that, right? My force is the total mass of the system times the acceleration that I need for the system. So once I've found that acceleration, it's really no more than just applying Newton's second law and saying what's the mass of the system and what's the acceleration that I need. And that's all I've done here. Obviously you could distribute this out if you would like to. I wouldn't mess with taking it any further than this. So I have an expression in terms of m1, m2, g, and theta that represents the force that I need to apply so that mass 1 does not slip down the ramp. Again, this was a very tricky question. What I would suggest is, obviously, if you've had to watch this video to get the correct answer, maybe make sure you can work it through a couple times without watching the video. And maybe see if you can consider what would happen then if I wanted this block to accelerate up the ramp or if I wanted it to accelerate down the ramp. So think about, obviously not necessarily writing an expression, but think about maybe the context that you would want for either of those accelerations. Just good thing to consider. If you do want any more help on this or any more questions like this, just come find me.